This is the October edition of our Roman Community Forum, and we're just about a year away from launch, so this is an exciting time. My name's Tom Barkley. I'm the operations scientist at the Roman Space Telescope. I think we've got a really exciting session today as we're going to learn about the definition of the Galactic Plane Survey. But before we get into that, I wanted to let Julie McHenry, our senior project scientist for the Roman Space Telescope, give you a quick status update.
Thanks, Tom. I wanted to talk about two things. The first is the status of Roman itself, and then a few comments on the Galactic Plane Survey itself. So on Roman, things are going really well. We are coming to the end of our major thermal vacuum test. This is the last major test of the observatory. We will be starting to warm everything up at the end of this week and move out of the thermal vac chamber in mid-October. The path beyond that is to put that major part of the observatory with its other half, the outer barrel assembly, solar arrays, and deployable aperture cover, some final tests, and then plan to send it to the Cape in mid-June. We are in the process of formally changing our official the launch date we're planning to from October 2026 to September 2026. So we're continuing to move early. So this is much earlier than the official date of May 2027. If you might be aware that the government is in a partial shutdown at the moment. We can all be here because the first day of the shutdown is part of sort of an orderly shutdown, and we consider this meeting to be part of closing things out neatly. We have an exemption to continue work on the thermal vac test, so that is continuing. But you'll probably see a little bit less of some of the Roman civil servants folks if this shutdown continues over the next few weeks. But we're hoping to be able to manage things without a hit in our schedule. So all positive words. And then the reason we're here, I'm incredibly excited that we're at the point of releasing publicly the definition of the Galactic Plane Survey. This was not part of the original plan. We had requests from the community to consider scheduling one of the general astrophysics surveys early, ahead of the first call for proposals. We had a process to decide what the scientific theme of that survey should be and whether we should proceed with defining a survey early. And that went through a committee process that recommended a galactic plane survey as the highest priority, closely followed by a deep field. We decided to proceed with the galactic plane survey. One of the key aspects of that was the compelling case that the people who wrote white papers made for the value of defining that survey via a community process and the value to the community in defining it early. And here we are at the finish line with a really nice defined survey with lots of careful thought and work. And I'd like to express my thanks to Bob and Rachel as the chairs of the committee, the whole committee for the huge amount of work that they've put in, and all the other people who've been involved in writing science pitches, white papers, in actively participating in workshops and meetings. I think this truly is a community survey that has been defined by and will be owned by the community. So with that, I will hand it over to Rachel and Bob to take it away. Thank you.
So thank you very much, Julie. And Bob, if you can share your screen.
I should be sharing it, am I not?
Okay, I'm personally not seeing it.
No, you're
No,
not anymore.
Hold on a second. Let me try again. I see what happened. Yeah. So, okay. Now am I sharing it?
Yes, now I see it.
Okay.
That's
Slide.
great.
Okay.
Okay, thank you very much. So, hello everybody, and thank you for the opportunity to tell you about the Roman Galactic Plane Survey report. My name is Rachel Street, and as Julie said, I am co-chair of, with Bob Benjamin, of the Galactic Plane Survey Design Committee. Next slide, please. So let me first introduce the members of that committee. All of the people that you see on screen were selected from self-nominations and invitations in order to make sure that we had expertise on a wide range of topics, and that reflected the wide range of science cases that were put forward by the community. Bob and I are deeply indebted to the whole committee for all of the hard work that they put in throughout this whole process. Together, they represent a huge amount of expertise on all areas of galactic science, and it really has been a great experience to work with them. Next slide, please. So the primary goal of this talk is to give you an overview of the final survey design, of course, and to talk in detail about all the different components of it. But we'll also explain the process of how we arrived at that conclusion based on the community input that we received. Next slide, please. So let's start with the overview of the survey. This slide shows the outline of the RGPS survey footprint in white, superimposed on an image of the Milky Way from the Gaia mission. And as you can see at a glance, we will cover a substantial fraction of the central Milky Way. Next slide, please. So if we look at this region more closely, the survey is composed of 3 elements, so we'll take a closer look at each one. First of all, the wide field survey extends from +50 to -80 degrees in galactic longitude, with the exact boundaries depending on the final mapping speed. And within this, there are 3 separate sections. There's a central band, 4 degrees wide, across the central galactic plane. This area will be observed with 2 filters in year 1 and in a different 2 filters in a second pass in year 2. And this region broadens out slightly at one end to cover more of the Carina region. Now, it's worth noting at this point that one constraint that we were given was that all observations had to be completed within the first 2 years of the Roman mission, hence the 2 passes in 2 years. The band widens out to ±6 degrees to cover the whole of the central Boulder region, and that area will be observed in 3 filters. And there's an additional region added to include the W40 Serpens South field, which will be observed in 5 filters. Now, in addition to the wide field area, that we have selected 6 subregions within that footprint for cadenced observations in order to serve the many time domain proposals that we received. Those areas are highlighted in cyan, and they will receive a single visit with observations in multiple filters, but a single filter will be used for most of the visits in order to achieve the required cadence. And last but not least, there'll be a total of 15 fields which will receive deep spectroscopic observations in all filter pass band plus the spectroscopic bands. These fields were deliberately spaced out across the galactic plane to cover areas with different stellar densities and different stellar environments. Those are shown in orange on the plot, and Bob is going to talk more about those regions later on. Next slide, please. So here are some key takeaways on the survey. First of all, it's going to be the deepest near-infrared survey of the galactic plane to date, and it will use all of the filters except F146. The limiting magnitude that it will reach obviously varies as a function of filter, transmission, and extinction, but also as a function of survey strategy. So remembering that the bluer filters will be used primarily for the deep spectroscopic fields. The wide field survey will typically reach a limiting magnitude of about 23.1 in F129, and that's roughly equivalent to J-band. The saturation limits also vary depending on the survey component, but for the wide field survey, the brightest object in J-band will be around 14.3. And that will be delivered for an area of 691 square degrees across the galactic plane. And Bob's modeling of this region based on the Trelegal galactic model suggests that it will include at least 14 billion stars and up to 20 billion in some filters. Now that's a significant fraction of the total population of the galaxy. The plot illustrates how the RGPS will compare with other surveys, and it shows it's extremely complementary to the Rubin Observatory Legacy Survey of Space and Time, with a similar sensitivity to that of a Rubin's single visit depth.
Oops, did I just jump
We've
out?
stopped sharing, yeah.
Yeah, okay, let me try again, sorry. Okay, I don't know why it booted me. So I'm trying to share. Okay.
Okay, great, thanks. And if you could go on to the next slide. Thanks. So to put the RGPS in context, this will be the first general astrophysics survey that Roman will do, but it dovetails very well with the core community surveys as well. So the core community surveys include programs that are dedicated to both wide area and time domain surveys at higher latitudes. In the galactic plane, the core community survey there was really a time domain study focused on the galactic bulge, but that really focused on a very small region. So with the addition of the RGPS, we now have wide area and time domain surveys at both low and high galactic latitudes. And it's worth noting that the RGPS will only take 7.4% of the time allocated for Roman general astrophysics surveys. So that leaves the majority of the remaining time available for proposals over the next 5 years. Next slide, please. So speaking to the survey definition process now, unlike the core community surveys, the RGPS had no associated project investigation team, and the timeline for this was relatively compressed. So to summarize that, the mission first solicited ideas for general astrophysics surveys in 2021, as Julia mentioned, and the galactic plane was strongly favored as a result of that process. So the mission solicited community feedback on what the scientific goals should be in the form of white papers and science pitches in early 2024. Our committee was formed in the fall of that year and tasked to evaluate the community contributions, and our report based on that evaluation was submitted to the ROTAC in August. Next slide, please. So we received 9 white papers and 32 science pitches in the initial call for input alone. And they covered a very wide range of science topics, from solar system science to young stellar objects and star-forming regions, stellar clusters of all kinds, galactic structure, and even extragalactic targets. Notably, we received quite a number of time domain proposals that focused on variability of all kinds. And we felt a table of all of these papers would be overwhelming for one slide, so you can see a little video of them scrolling past at the bottom there. And I'd like to take this opportunity to thank everybody who put effort into all of these contributions. They really influenced the design process, and they were fantastic to read, so thank you very much. Next slide, please. So once the committee had reviewed the initial round of input, we drew up a preliminary survey design, and that process allowed us to identify a number of key trade-offs questions, such as the filter selection and the area versus time trade-off. So we organized a virtual workshop in February of this year with 2 goals. Firstly, to give feedback to the community on the progress of the design process so far, and also to solicit input on those key questions. This was a very rewarding event. We had 260 people pre-registered to participate from all across the world, so a huge amount of interest. And we structured the agenda to really encourage feedback. We obviously had a few formal presentations, but most of the workshop was dedicated to breakout sessions where we specifically invited the community to discuss the key trade-offs that we needed to make. As a result of that workshop, we actually received some additional science pitches from the community, which we also took into account. Next slide, please. Now, in the interests of verifying that our preliminary designs would actually serve the needs of the science that had been proposed by the community, it was important to ensure that we properly captured the requirements of the science. So we reached out to the authors of all of the contributions to make sure that we were doing that. And we have a working group dedicated to creating metrics or statistical criteria, which the committee then used through the design process. Now, the metrics necessarily focused on a limited set of key observable parameters. Those included the survey footprint, the number of stars within that footprint, and also the number of specific objects within that footprint, such as classes of objects like stellar clusters, for example. Proper motions were key to many of the science cases, as were the number of objects observed in different filter band passes, so we have a metric for that. And we also had a metric for evaluating the number of visits to each point in the sky with respect to some of the time domain proposals. Next slide, please. So this analysis quickly showed that sky region was going to be the defining characteristic of this survey. So these graphics show the combined regions of sky that were requested by all of the science cases plotted for different filters. And the colors are scaled by the number of proposals that requested each HEAL pixel. So a deep red color indicates that a lot of science can be done with observations of that area of sky. And from the F158 plot, you can clearly see why the wide field survey focused on that central region of the galactic plane. However, the community adopted a rather liberal definition of galactic plane, as you can see from the F213 plot. People asked for observation. Oh, we've lost the slide again.
Gonna share again. So there we go. I don't know why it keeps doing that. I apologize.
Okay, that's great. Thanks, Bob. So looking at the F213 plot, you can see that people asked for a combined region of over 36,000 square degrees. And we didn't have nearly enough time to cover that whole area, much as we would have liked to. However, in fairness to the community, many of the proposals indicated that observations of some of the requested regions would be valuable. They weren't necessarily asking for everything. And so this motivated the committee to design both the wide field area survey and then add in observations of smaller regions of specific interest. Next slide, please. And at this point, I will hand over to Bob to talk more in detail about some of the trade-offs that we had to discuss.
Right.
Go ahead.
Probably one of the most important trade-offs we had to decide was the number of filters we would use for a given area of the galactic plane. The plot on the left shows the number of filters requested for various science cases. So you can see that, for instance, 20 science cases could be satisfied with just a single filter. But there was a clear break point at 4 filters, particularly programs that were looking in the galactic plane where you needed to do extinction corrections or SED studies, really seemed to require 4 filters. So that was our sort of initial message of the community. And 3 of the filters, both on the committee, but also community response, were very clear. Essentially, the equivalence of the J, H, and K filters, which would be the F129, which I've mislabeled here, I see, F158, and then F213. The 4th filter was was more challenging to decide upon. Initially, the community was evenly split on the question of just using the F106 filter, so the shorter, bluer part of the spectrum, or the filter that fills in between H and K, the F184 filter. And our investigations of which filter would be more effective for SED and extinction analysis were inconclusive. So we are actually continuing to look at this, but based on the evidence we had and the science pitches we need, we decided to go for the F184 filter over the F106 filter because we really could only cover enough. Covering having more than 4 filters would cut down the area too much. So notice that the combined with Rubin and the Roman Galactic Plane Survey will have basically coverage from the U filter in Roman all the way to the F213 filter in Rubin and Roman, and this includes the F184 filter. There will be an unfortunate region of low transmission. You'll see there's a little bit of transmission in the Y filter in this region marked on the left, and a little bit coming up in the F129 filter. But by excluding the F106, we are leaving a bit of a gap. However, the F184 filter was preferred for several reasons, including the Paschen alpha feature, which is useful for the ISM and accretion, looking at stellar accretion, the water absorption features for looking at low mass stars, and the fact that the F106, even though it's low transmission, is partially covered from the ground. So we just selected the F184 filter. It was the committee decided, and also based on the community input, that a contiguous design was important. In order to get many of the nearby star formation regions are off the plane, but Serpens South was close enough to the plane. This little bump here on the left here, that it was added to the Galactic Plane Survey. It's approximately the same distance as Orion, but 1/5 the star formation. Unfortunately, this decision to make sure the area was contiguous did affect the ability to include some programs, particularly the Kuiper Belt field and other nearby star formation regions that are too far from the galactic plane. So these are areas of science that could potentially be subject for other guest astrophysics or general astrophysics surveys. Their survey is asymmetric. Partially, this is because of the nature of the galaxy. It covers most of the intergalaxy star formation from the Sagittarius tangency to the Carina tangency. There's a lot of star formations been grouped into that arm. In addition, the Rubin data is available for the full area, although the monitoring is less from 30 to 50 degrees. The plot here shows basically the number of Rubin visits over a 10-year period. And you can see that most of the Galactic Plane Survey lies in the regions that are shaded more blue, which indicates a greater frequency of monitoring. Also, the Carina region was just very popular. If we had to stretch to the one way or the other from Galactic Center, the Carina area had much more scientific interest. The survey depth is indicated by this plot. This shows a simulated color absolute magnitude diagram in the direction of L of 5, B of 0 with the trilegal model. So you can see the main sequence. You can see 2 main sequences because of the binaries, the red giant turnoff, and so on. And the distance range over which certain classes, oops, I've lost this thing again. So let me exit and restart. Sorry about this. This is not interacting well with Google Slides, apparently. So slideshow, hold on. So, okay. If assuming an extinction of 1.6, which is typical for the mid-plane in the inner galaxy, red clumps can be seen out to between 3 and 173 kiloparsecs. Solar-type stars, you can see down here, can be detected out to 20 kiloparsecs. M dwarfs to the distance of galactic center, early M dwarfs, M zeros, and L dwarfs out to about 600 parsecs. There were some science cases that wanted deeper observations than our sort of standard mode. There was particularly interest in getting this main sequence turnoff in the bulge with high signal to noise, also brown dwarfs in nearby star formation regions. For those regions, there will be deeper fields because of our time domain and deep spectroscopic observations. So the deepest observations of the Roman Galactic Plane Survey will be in the direction of the nuclear stellar disk, where we have 61 minutes in F213 and 18 minutes in F129, and then basically 60 minutes approximately in 3 filters in the a single pointing towards W40 and Serpens South star formation region. The timeline is tricky because this shows a plot of observability as a function of time. So this is a space-time diagram where space is on the horizontal axis in terms of galactic longitude, and time is on the vertical axis. And the ovals are regions where the galactic plane is not observable. So you can see that essentially the galactic plane is observable for a few months each, every a few months twice a year. And of course, the central region here is where the Galactic Bulge Time Domain Survey will be using a lot of time. So our recommendation is that obviously we'd love to get the Galactic Plane Survey first pass done as quickly as possible. This would be F129 and F213. So the community has a lot of J and K data, essentially, to make color magnitude diagrams. Um, and in an ideal world, the first pass could be done even before the Galactic Bulge Time Domain Survey. There's 2 days that have been recommended to be preserved for the Galactic Plane Survey to map through here. And then you could finish off the Galactic Plane in 4 days. Given the pressures on Roman for scheduling, it's not clear that this will happen. The late first pass would end up wrapping closer to fall of 2027. And then the second pass would happen at a time where the Galactic Bulge Time Domain Survey would not be observing the central galaxy as extensively. So in principle, the second pass could be completed by May 2029. This, of course, all depends on the scheduling of all the other programs, so there's no promises here. But note that if you're interested in proper motions, even with the first pass, proper motions can be studied with data from prior programs like 2MASS, VVV, and Hubble. So in terms of the other elements of the programs, I'm just going to say a little bit. So we have the time domain regions that are, there should be 6 regions totaling 19 square degrees, observed for 130 hours, which is 19% of the total time for the program. This will consist of imaging in all 7 filters, except for the Serpent South region, and then monitoring in an individual filter. The deep spectroscopic pointings will total 4 square degrees. They're just individual Roman pointings spaced along the plane. Again, both of these regions will be panchromatic, so you'll have all the filters. But the deep spectroscopic ones will go deeper in all the filters and also include GRISM and PRISM observations. In terms of the observing strategy, for most of the mapping of the wide field, we're going to be using not dithering, but just using a gap filling strategy. So it's basically just 2 observations. This means that there will be uneven coverage of the galactic plane. There will actually be about 1% of the wide field that will not be covered in a given filter. 28% covered once and 67% covered twice. This is a matter of concern, and the committee will be looking at the data quality, particularly for the n=1, where we only have 1 image to work with, to see if this is a viable strategy. And the report details some contingency plans. The box gap 8 region, which will be used for time domain regions, some of the time domain regions, and all of the deep spectroscopic regions, of course, gets much, much better coverage, and on average goes about 4 times deeper. So the time domain regions are shown outlined on the galactic plane up above, from Serpens to the W43 on the left all the way to Carina. In terms of the cadences, the committee struggled with this to find cadences that would satisfy different cases. Ultimately, and I've been booted out again, so exit, share again. And start again. I'm getting faster at this. So ultimately, we selected sets of cadences, high cadence visits. This is basically using the Galactic Bulge Time Domain Survey mode, but for much shorter periods of time. And so that'll be roughly 11 minutes cadence cycling among 6 fields for a total of 8 hours with 43 total visits. Then we have a set of hourly visits for certain fields, hourly where the spacing changes over time. This is actually a strategy inherited from a Spitzer YSO program, and that will be used in the Serpens region and the central molecular zone. And then the central molecular zone will also be monitored, and the nuclear stellar disk will be monitored in 2 filters for weekly for up to 2 months. So you can see in this table here that the central molecular zone in the nuclear stellar disk is going to get a lot of love in terms of time domain cadence, time domain coverage, which also means they'll be much deeper images. Most of the fields will have high cadence, and then Serpens will also be these hourly cadence. So this just shows the location of the footprints in cyan, located on a Spitzer image of the central molecular zone. The gap in between the left and the right is where the Galactic Bulge Time Domain Survey will have its observations. So essentially, the Roman Galactic Plane Survey will provide flanking regions to try to get the entire structure of the CMZ and nuclear stellar disk, with less temporal coverage but more aerial coverage. So again, high cadence, hourly, weekly, and of course, since this will be re-imaged in year 1 and year 2, you can also assess variability over year-long timescales. Serpens South is a slightly different beast. It's only going to be covered with this hourly cadence over a bigger area. And the yields, both for the high cadence and the hourly strategies, are discussed in the report. The additional element we have here is the spectroscopic element. This will be 15 single Roman pointings observed to 4 times the nominal depth using the box gap dither, plus the 5-minute Grism and Prism observations at 2 different roll angles. These were spaced along the galactic plane with a range of stellar densities and diffuse emission, and they were selected from a heat map generated from the community input that Rachel collated of community requests. So we tried to make sure that there was something for everyone in these little deep fields. So we have 6 star formation regions ranging from 400 parsecs to 6 kiloparsecs, 4 fields with open clusters, some of them with multiple open clusters, 2 fields with IR extinction windows, 1 field with a large angular supernova remnant W44, 1 field with the SCO-SEN group, only at 100 parsecs away, including a stellar wind bow shock around Alpha Crux, and 1 field with 2 globular clusters, 1 near and 1 very far away from us. So these are just sort of, as I mentioned, W40 got some special treatment, being the nearest star formation region in our survey. So that will actually be observed for 60 minutes each in just the 3 filters and just the prism observations, since there was and the positions of these fields will be tweaked depend on the scheduled roll angle, just to line them up as best as possible with the data that we already have on these regions. But we hope that this data will be useful for planning future spectroscopic or deeper coverage of the galactic plane, and allow people to look at the use of the Grism and Prism in fields with a wide range of stellar density and diffuse emission. So I'll just end with a couple thoughts getting ready for the RGPS. The call for proposals and for the analysis of these data, plus additional general astrophysics surveys, is expected this fall. I'm providing a link from this newsletter that it's a nice compilation of all the different ways you can get involved. The RGP Roman Galactic Plane Survey report will be posted on archive soon, and I think it's already available on some of the Roman websites. And you can feel free to contact committee members if you have further questions. Finally, I wanted to mention that a subset of the definition committee actually decided to request director's discretionary time of JWST NIRCam images of 7 fields along the galactic plane, which will allow us to basically serve as pilot investigations. And also, the committee will be looking at this to confirm the use of different filters for constraining stellar parameters. But this data is free to the public. It's all been observed in the last few weeks. It's program ID 9438, and Eddie Schlafly led this effort. And the picture here just shows a beautiful star formation region 20 kiloparsecs away from us through the galactic plane. So it's really quite amazing what can be done with Roman in general, but Roman and JWST in particular. So to conclude, the graphic here has this recommended survey design for the Galactic Plane Survey with all the elements. It should allow for wide field, time domain, and deep field spectroscopic science. The ROTAC has reviewed plans and provided comments. The cycle 1 call for proposals, including the data analysis of this program, should be available in fall 2025. The first pass could be completed by 2027, with the second pass coming in mid-2029. But this, of course, will depend on the scheduling of all the other program elements for Roman. So thank you very much, and I'd be happy to answer questions along with Rachel.
Thanks, Bob. That's great. Really, really exciting stuff. We certainly have plenty of time for questions and a really good turnout for this. So hopefully there'll be folks who want to ask questions, but that was an excellent presentation. So the floor is open. Okay, question from David.
Hey, can you guys hear me?
Yep.
Great presentation, really exciting stuff. I was just curious if you guys calculated what depth we can get to with the deep spectroscopic observations.
We have calculated. I can't remember what number to give you off the top of my head. But I mean, essentially, the table that we have here in there, and we have a table in the report that gives you the sort of the depth for the nominal observations, and so just at 0.75 magnitudes deeper for the deep fields, and then of course even deeper for the time domain fields where we have lots of coverage in certain filters. So, but I can't tell you what the magnitude limits are off the top of my head.
Okay, thanks.
Okay, question from Sanjeev.
Hello, yeah. Yeah, similar follow-up question on spectroscopy. I guess the most uncertain factor is at what crowding level can we do spectroscopy properly. So I see most of the deep spectroscopic fields are in the plane. They go wide in longitude, which means we can probe different density regions. But I was still worried, let's say, even in those regions we don't find, do we have like a backup thing, like a slightly less dense field to make sure that there is certain area we know where spectroscopy would work? Yeah, just some thought.
Rachel, do you want me to do that one, or shall I? Or do you want to?
Be my guest.
Okay. Yeah, so I mean, this is a real challenge because I think a lot of community members were very excited about the potential for spectroscopic observations, but are not clear how how well this will be, how well sources can be extracted in crowded fields. Essentially by going out to the maximum longitude extents, we went out as far as the lowest stellar densities we can. I suppose we could have put a pointing sort of at the largest longitude and the largest latitude, but I think at that point if it fails elsewhere, I mean, if you can't get useful information in those intergalaxy fields, I think it'll be less attractive to do a spectroscopic program that follows up on this. So I guess the bottom line is we don't know how well this is going to perform, but the community definitely wanted to see what this data would look like, and we tried to provide a range of environments for people to test it. So,
Thank you.
And if anyone out there has looked at the issue of the spectroscopy with the Grisman prism in crowded environments and has sort of started to do investigation, we would love to hear more about that because I think a lot of people would want to know it. So.
Okay, any further questions for Bob and Rachel on the team? I don't see anything else. I put a
There's
link.
online question.
There's an online question. You mean in the chat?
I don't know.
I think somebody raised a hand. I don't know if that was raised earlier.
Sanjib, who I think has already asked his question.
Yeah, so there was a question about the Roman science users panel, and I think the answer there, Julie answered, but there's no update yet. We have yet on the status of that, but we'll announce when there's information to share on the selections there. In the chat here, I put a link to our Roman Community Forum page. But for those of you who probably got the email, and that's why you're here, there's a link to on that page. There's a link to the report, and we're expecting that report to be on archive shortly. But for the time being, you can find it on our Community Forum page. Daniel Huber, you want to ask a question?
Yes, can you hear me? Okay.
Yep.
I don't actually have a question, but a follow-up on the spectroscopy stuff, because we thought about it as part of the Galactic Plane Time Domain Survey, and the answer is that there has been a bit of work on that definition committee that was led by Hans-Walter Rix about disentangling spectra in very crowded environments, and the results look quite promising, but which is one of the reasons why we decided to include a spectroscopy component there as well. But I just want to emphasize what Bob said. I mean, this is an interest. The science yield from both the GPS and the GBTDS would be multiplied by a lot if we can make this work. But I think it's up to the community to make it work. I think there's technically there were some concerns about guiding, which I think have been mostly retired now. Perhaps someone in the Roman project can weigh in, but I think in terms of actually using the data, I think it's up to the community to do something clever and use the spectra. I think we estimated a crowding limit where this will be possible to get reasonable RVs and metallicity and so on and so forth of stars down to 16th in K-band.
Right. And we agreed with that analysis. So the 16th magnitude is sort of where you hit your limit, which is a good number because it's the typical magnitude of a red clump giant in the galactic bulge. But yeah, the dream here is that maybe this could pave the way for a future spectroscopic investigation of the galactic plane, where you would be able to constrain stellar parameters in a much more detailed way than just with the photometric analyses.
Yeah, just very quickly, we did it within the project Explore, guiding in crowded fields, because it was initially some concerns that we could actually even point the spacecraft stably in those fields, and the analysis is very, very positive, and it's looking likely we will be able to technically look in those locations. Although, as Dan said, the analysis of the data is the community's challenge to work with.
So this will provide data for people to work on. So.
All right, a question from Mario Gennaro.
Yes, hi. Well, first, thanks a lot. This was a very, very nice presentation, very clear. I wanted to go back to the slide you had on the basically competing resources with the Galactic Bulge and Domain Survey, and ask you a little bit about the.
I mean, it's wrapping up anyway. So yeah.
Oh, sorry. Somebody
questions that would be helpful regarding shutdown things. Not that I know a ton. But...
No?
Sorry, we had some crosstalk there. Go ahead and continue the question.
I was going to ask you if you could pull back the slide where you started talking about competing scheduling, let's say, requirements with the Galactic Bulge Survey. Is there a science requirement on proper motions or some variability that you have in mind in order to set some of the constraints on the first epoch?
Yes.
I'd like to hear a bit more about the scientific rationale and accommodation that can be made. I'm with two hats here, both interested in the science and in the implementation aspect.
So let me just share the slide you're referring to.
Yes, this one.
So let's see. For some reason, I've lost my control, so I'll just leave it like that. So as you can see, basically doing the galactic plane, given the observability, is sort of threading the needle here. But the Roman maps so fast that you can basically go through this region very quickly. If, for instance, the first pass early arrow is not possible, then we would be wrapping up, and again, I don't even know if this will be possible, but the first pass late scheduling could get you finished just before the second galactic bulge season. We did argue about this. In other words, obviously for proper motions, the longer the baseline, the better the proper motions. But the longer the time, the more the community is waiting for it. And the ultimate value of the proper motions we hope will come in some future observation of the galactic plane, 5 years later, for instance. So we decided that although it's not optimum, somewhere 2 years would give you a proper motion uncertainty of about 0.4 milliarc seconds per year for bright sources. It starts to degrade a little bit. I mean, as if it were a year and a half baseline, but not so much that we felt like we needed to request that they push it one bulge season later. And so it's, essentially, I think that the desire to get the data out to the community in a timely way is outweighed the desire to get slightly improved proper motions by waiting half a year or a full year. So that was a challenge to discuss, though. Did that answer your question?
Yes, thank you.
Okay.
Yes, I can.
Oh, go ahead. Sorry, Julie.
Yeah, I was going to comment on the data release. So the Roma data policy is that all data are released as soon as they're processed. But you've also asked, how do you know what's going on? So Slack is certainly one way, but I was wondering if somebody from the SOC could comment on how a person could sign up to receive notification about the progress of observations on a particular survey, because my understanding was that there was a way to be notified if data from a survey had appeared in the archive.
I don't know. Carrie's here. I think maybe she knows better than I do. Oh, Christy's also here. I think. Okay, I'll let. I didn't realize.
I'm here, but
Christy,
I don't have a direct answer. I don't think. I don't know of a directly or a simple way that's already implemented to do that. So I'd have to dig a little bit. It's not obvious to me the process of how that would work on core community survey observing programs. So yes, this is done for other missions when you have PIs, but of course this isn't the same structure. So the answer is I'd have to get back to you, Julie. Don't know. And I don't think Carrie, who's sitting right next to me, you don't have any other, no other insights. It's not something that I have thought about in advance.
Another question I noticed on the chat was someone was simply asking is, will the Galactic Plane Survey channel on Slack be the principal way in which galactic plane information will be shared? And I don't think we anticipated that we would run this channel as sort of the Galactic Plane clearinghouse going forward. I'll certainly post things that are of interest from as time goes on. But for people that are interested in keeping contact on galactic plane projects, I certainly could recommend the Roman Science Collaboration. And there's information on the Roman websites about that. So there is a collection of people that are trying to sort of coordinate projects and ideas. And I plan to basically move a lot of my updates to that environment, as opposed to running a separate Galactic Plane channel on the Roman Slack.
Thanks, Bob and all for that one. Zach.
Yeah, I can just say from the MAST side, there will be a subscription service that people can sign up for that lets you basically subscribe by program ID. And so that's still in development. I'm not sure off the top of my head what the timeline for deployment is, but in time for launch. But if people want updates for any new data from the core community surveys, or anytime something gets reprocessed, there will be options for that in that subscription service.
Amazing, Zach. Thank you for filling in the gaps for us. And for those that are on the call, Zach is part of MAST, and this would really be a service provided by MAST, the archive. So thanks so much for filling in the gap for me. Appreciate it.
Of course.
Yep, thanks, Zach. That's great. Okay, any more questions for the for us or from the mission or Bob and Rachel or anything else? Okay, I don't see anything. So it looks like we can call this a meeting. So thanks everyone for joining us. This is really very, very exciting. We now have 4 surveys defined, and we're 1 year from launch. So data's going to be in hand sooner than you think. So thanks a lot, everyone, and we'll call that a meeting. Bye.
Bye, everyone.